So we previously looked at particles moving on smooth planes and particles moving on rough planes, or particles in equilibrium on rough planes. But let's consider particles that are actually going to be moving on rough planes now. So if a particle is held at rest on a rough plane which is inclined to the horizontal at an angle alpha. So if this is a rough plane, we have an angle alpha here. And we have tan alpha is 3/4, which means that our triangle is going to be in this ratio, 3/4, which means this is 5. So we know that we can therefore get that what sine alpha is 3/5, and cosine alpha is 4/5. And that's going to prove useful, I imagine. The coefficient of friction between the particle and the plane is 0.5, and the particle is released and slides down the plane. So we have our particle, and we're not given a mass in the question. It doesn't seem. We know that we're going to have a normal reaction force, and we're going to have mu r here, which is going to equal 0.5 r. We're going to have a mass of m, because we don't know what it is. So the weight is mg. And this is a nice question because it's got a lack of numbers, so you have to just to go along with, well, mg, r, and you give them what mu is. That's really that, and the angle is the only information that you're given. However, from what we know about how we deal with particles on inclined planes, we can look at the resolving forces perpendicular to the plane and parallel to the plane. So if we look at perpendicular to the plane first, our mg has, where this is alpha, has a component that is perpendicular to the plane and a component that is parallel to the plane. And the perpendicular component is going to equal r because this particle isn't going to be lifted up off the plane. So that perpendicular to the plane part is going to be the same as our r. But that is also going to equal mg cos alpha. That's going to be our short length, mg cos alpha. And we know that cos alpha is 4/5. So it's going to be 4/5 mg. So now we know that r is 4/5 mg. And we know that 0.5 r is 2/5 mg. That's helpful. So let's just consider then the perpendicular to the plane components of the forces here. We already did actually. So we got that r equals 4/5 mg. Now, if we look at the parallel to the plane components, we have this component here. Well, that's going to be equal to mg sine alpha. Now, sine alpha is 3/5. So this is going to be 3/5 mg. All right. And you can see that if I make sure I put in directions for these forces, the weight has a component that heads down the slope. So if we're thinking about up our slope being positive, then 0.5 r, or 2/5 mg, is going to equal our components going down the slope. Well, it's not. Sorry, my bad. It's not going to equal. You can see they're not. You can see they're not equal, and it's not equal because you can tell that. Well, we already knew from the question it's going to accelerate. Because we've got unbalanced forces, we're going to accelerate down the slope. So instead of taking up the slope as being positive, let's take down the slope as being positive, because that's where we're going to accelerate. And down the slope, we have a force of 3/5 mg. But we have frictional resistance of 2/5 mg. But that equals our mass, which is m, times by our acceleration. At this point, you can see that every term has m in it, so we can cancel out the m. And 3/5 g minus 2/5 g is 1/5 g. So our acceleration is 1/5 of g, which means that our acceleration is 1.96 meters per second squared. Because we now know the acceleration down the slope, we can use, and that's a constant acceleration, we can use Suvat's equations to then figure out the distance it's going to slide in the first 2 seconds. That's what we're trying to find out. We start from rest. It's released and slides down the plane, so it's being held. Where does it say it? Particle is held at rest, and then it's released and slides down the plane. So its initial velocity is 0. Again, we're taking this way as positive, making sure I think about that. Don't know what the final velocity is. The acceleration I've now got as 1/5 g, and we're looking at the first 2 seconds. So you can see S, U, A, and T. So S is UT plus half AT squared. So X equals 0 times 2, which is 0, plus half A. Well, half of A is 1/10 G times T, which is 2 squared. So that's 4/10 of G. So 39.2, so 3.92 meters. That's how far it would travel in the first 2 seconds.